Ever get caught in one of those surprise downpours? You know, the kind your weather app totally missed?
Oh.
Or maybe you're like me, planning a vacation months out, hoping for, fingers crossed, clear skies.
Yeah, we always need a good weather forecast.
It's funny, right? We rely on them constantly.
Mm.
But getting those forecasts right, especially looking further into the future, it's a challenge. Even for, like, the top minds in science.
It really is.
And it's not just about dodging raindrops or planning that perfect beach day. Predicting our climate, the long-term, patterns of our planet's atmosphere, well, that's crucial for everything. I mean, everything from understanding global warming to even, like, preparing for food shortages. Big stuff.
Absolutely. It impacts everything.
Now, for the longest time, the real heavy lifting in all this weather and climate prediction has fallen on these things called general circulation models.
Yeah.
GCMs is the shorthand you usually hear.
Right, GCMs.
But picture it. It's like this massive simulation of the Earth's atmosphere, crunching tons of data, complex equations.
Oh, yeah. Incredibly complex.
But GCMs, they're sophisticated, but they've always had their limits.
Yeah, and it's interesting. One of the things is these traditional models, they actually need a surprising amount of just manual, like, fine-tuning.
Manual. Wait, you mean like someone's in there actually tweaking settings?
Almost. Think of it like calibrating a super, super sensitive instrument. You have hundreds of parameters that someone has to adjust, which is, first of all, incredibly time-consuming. And honestly, it's just impossible to get rid of human bias completely.
So you're saying there's this human element baked in that could be affecting their accuracy.
Exactly. And that's where these neural GCMs come in. It's this totally radical new approach that combines those physics-based equations with, get this, the learning power of AI.
So we're basically, like, teaching a computer to read the weather. Is that right?
That's a great way to put it.
So how do you even begin to do that?
Well, at its core, neural GCM, it's a hybrid. It takes the best of both worlds. So it merges what we know about physics from GCMs and then adds in that pattern recognizing ability of neural networks.
Okay, so it's like a tag team.
Exactly. A tag team.
I like it. So who are the partners on this tag team?
So first up, you've got the differentiable dynamical core. This is the physics powerhouse. This is what handles those fundamental forces that govern the atmosphere, gravity, the Earth's rotation, all that good stuff.
Gotcha. So that's like the solid, reliable foundation.
Right.
Who's the flashy newcomer?
That would be our Learn Physics module.
Yeah.
This is where that neural network really gets to shine. So imagine you're feeding this AI massive amounts of real-world weather data. We're talking decades worth of information.
Yeah.
A data set called ERA5.
You're A5. Does that sound ominous to you? Sounds like a weather event in and of itself.
It does, doesn't it? But don't worry, it's nothing scary. It's basically just this comprehensive record of all different kinds of atmospheric variables.
Okay.
But the key here is the neural network. It devours this data. And it's learning to predict those really, I'd say, finicky, small-scale processes that traditional GCMs they often have trouble with.
So things like cloud formation, precipitation,
Yeah.
those are notoriously difficult to predict, right?
Exactly. Those are the ones.
Yeah.
Because those are really hard to pin down with just equations alone. But the AI in neural GCM, it can pick up on those subtle patterns, the relationships within the data, and it adds this layer of nuance that those traditional models just miss.
So we've got this, like, supercomputer, right? And it's stuck with all these physics equations, and we're feeding it this constant diet of weather data. But how does it actually learn? Like, how does it make sense of it all? It's not like we're showing it a picture of a storm cloud and saying, all right, predict that.
You're right. It's way more nuanced than that. Actually, one of the most, I'd say, intriguing things about neural GCM is how they train it, the method they use. It's called the single column approach.
Single column. That almost sounds, I don't know, limiting for a model that's supposed to be simulating the entire planet.
It does sound a little counterintuitive.
Oh.
But it's crazy effective. Imagine, like, if you were looking at a core sample from the Earth, right? That single column of material can tell you a ton about, the composition of that specific spot.
Okay, I see where you're going with this.
Oh, so neural GCM, it does something kind of similar with the atmosphere. It'll focus on these vertical columns of air and analyze how, say, the temperature, humidity, wind speed, all those factors, how they change from the ground all the way up to the stratosphere. It's like creating this like super detailed profile of each atmospheric core sample, you could say.
So instead of trying to look at the whole planet at once, it's breaking the atmosphere down into these like smaller, manageable chunks.
Exactly. And by studying each of these individual columns, the AI starts to learn the underlying physics, the relationships between all those different atmospheric variables. Like, imagine putting together a giant jigsaw puzzle, right? Each of these columns is like a piece.
And the neural network, it starts to see that big picture emerge.
Yes, and that's how it builds this, like, comprehensive model of the Earth's atmosphere piece by piece.
That's really cool. Okay, so we've got this powerful hybrid model now, trained on like mountains of data. But how does it actually perform in the real world? Like, can it go head to head with the best weather models out there, the ones we always hear about?
Well, that's the question, isn't it? So the researchers, they put neural GCM through a whole battery of tests, compared it head to head with some of the best physics-based models out there.
How'd it do?
It was impressive.
Yeah.
They started by looking at medium range forecasting, so predictions up to 10 days out. And get this, even with what they call a coarser resolution than some of the other models, neural GCM performed as well, sometimes even better than those leading physics-based models.
Hold on, rewind. Coarser resolution. What does that even mean?
Oh, good question. Think of it like a digital image, okay?
Yeah.
So coarser resolution means you have fewer pixels.
Okay.
So in this case, it means that neural GCM was actually working with less data than some of those other models.
So it's doing more with less.
Exactly. And what's really key here, that efficiency means it needs less computing power. So that makes neural GCM faster, more accessible, especially in parts of the world where, computing resources might be more limited.
That's amazing. So not only could it be more accurate, it could make those accurate forecasts available to way more people around the world.
Exactly. It really could be a game changer. And it gets even better. Neural GCM also showed this amazing ability to predict, like, specific weather events. For example, it did a really great job with hurricane tracks, something that traditional models often struggle with. And it also realistically simulated those seasonal cycles, things like monsoon patterns, which are super important.
Wow, so it's not just getting those broad strokes, it's also capturing the details that really impact people's lives day to day.
Yes. And here's, I think, where it gets really interesting.
Yeah.
What makes neural GCM really stand out is its ability to generalize.
To generalize.
Yeah, they tested it by having it predict weather patterns for years that it had never even seen before, years outside of its training data.
So it's not just memorizing past weather, it's actually learning the underlying physics of how the atmosphere works.
You got it. And that ability to extrapolate, to make these accurate predictions about the future, even a future it wasn't specifically trained on, well, that has huge implications. And not just for weather forecasting, but for how we understand climate change, too.
Okay, so neural GCM, it's got potential for, figuring out if we'll need an umbrella next week. But what about the big picture? Like, can it help us understand these long-term shifts we see with climate change?
The million-dollar question, right? And honestly, the research, it's still early stages, but there are some really promising signs.
Oh, like what?
So, for example, when they feed the model historical data about sea surface temperatures, going back in time, neural GCM, it was able to accurately reproduce past temperature trends globally.
So it's like it can look back in time and basically recreate past climates.
Basically, it's a really important first step because it suggests that this model, it can do more than just predict weather. It might actually be able to model those complex interactions that drive climate change.
Right, but the real challenge is using it to look ahead, right? To project what those future climate scenarios might look like.
Exactly. And that's where things get even trickier. Accurately modeling the future climate, especially with so many factors changing at once. Think greenhouse gas emissions, for example. That's a big one that requires, a lot more research. We need to keep developing what neural GCM can do.
It's like trying to predict the outcome of a game when the rules are constantly changing.
Yeah, that's a great way to put it. But even with the challenges, the potential here is huge, incredibly exciting. It gives us this totally new way to approach these really complicated questions. And it could change how we understand the planet's climate system completely.
It's mind-blowing. So what's next? What's the future hold for neural GCM?
Well, I think the possibilities are pretty much endless. Imagine a world where those weather forecasts are even more accurate, more timely. especially when it comes to extreme events. Things like hurricanes, droughts, floods. Being able to predict those with more accuracy could save lives, not to mention resources.
That's a future worth working towards, for sure.
And it goes beyond weather, too. Neural GCM has the potential to revolutionize how we model the climate, which could then give us the tools we need to come up with much more effective strategies to deal with the impacts of climate change.
So it's not just about knowing whether to grab an umbrella anymore. It's about understanding the fate of our planet.
Exactly. And it gets you thinking, if we can apply this approach, combining these physics-based models with machine learning to something as complex as Earth's atmosphere, what else could we unlock? What other mysteries could we solve?
That's something to think about. Well, listeners, this deep dive into neural GCM, it's given us a glimpse into the future of atmospheric science. It's where artificial intelligence and physics collide to reshape how we understand the world around us. From knowing if we need that umbrella tomorrow to modeling the future of our planet's climate, neural GCM is changing a lot more than just the forecast. It's changing the entire game.